Alright, Lecture 2. Last time we learned the language. Open, closed, clopen. Today we put that language to work on examples, the way a tutor and a student would at a whiteboard. Stay with me. I'll ask the questions you'd ask yourself. Quick review from Lecture 1. Open means the set sits inside the topology tau. Closed means the complement sits inside tau. Clopen means both. If you remember only one sentence, closed is complement is open. Ready? Let's practice. No new axioms today, just detective work. Someone hands you a topology as a list of sets, and you figure out what's open, what's closed, and what sneaks into both camps. Example 1. For points A, B, C, D, and tau has 6 sets, empty, C alone, AB, CD, ABC, and the whole space. Student question first. What are the open sets? Don't overthink it. Exactly. The open sets are just the members of tau. That's the definition doing its job. Write them down once so your eyes see the list. Now closed sets. Tutor trick. For every open set, compute its complement in X and collect those complements. Empty complements to X, singleton C complements to ABD, the pair AB complements to CD, and so on. Notice something nice. AB and CD appear again. Those will matter for clopen. Clopen means in both lists. Empty and X are always there, plus AB and CD, because each is open and each is the complement of the other, so each is closed too. Student takeaway. When a topology splits X into 2 open pieces, both pieces are clopen. Example 2 is a little theorem in disguise. Claim, if every subset of X is clopen, then tau must be the discrete topology. Pause and guess why before we prove it. Here's the punchline. Clopen implies open. So if every subset is clopen, every subset is open. The only topology that contains every subset is the power set, and that is the discrete topology. Short proof, big idea. All subsets open is exactly discrete. Example 3. Cofinite topology on the integers. Reminder, a non-empty set is open exactly when its complement is finite. Empty is open by decree. Now we test 3 sets, like a quiz with a tutor sitting next to you. First, the even integers. Is the complement finite? No, the odds are infinite. So evens are not open. Is the set of odds open? That would need the evens to be finite. Also no. So odds aren't open either, which means evens aren't closed. Neither open nor closed. Common trap, infinite and coin finite, can both fail the finite complement test. Second set, integers without 1, 2, and 3. Complement is just 3 points, finite. So yes, open. Is it closed? That would require the 3-point set to be open, so its complement would need to be finite. But that complement is almost all of Z, infinite. So open, not closed. Third, -1, 0, 1. Complement is infinite, so not open. But the complement itself has finite complement, namely those 3 points, so the complement is open. Therefore our 3-point set is closed. Closed, not open. Nice mirror image of the previous example. Last claim, no non-trivial subset of Z is clopen in the cofinite topology. Suppose A is neither empty nor all of Z, and assume it's clopen. Then A and its complement are both open, so both have finite complements. Wait, carefully. Both A and a complement must be open, so each is empty or has finite complement. For non-trivial sets that forces both A and a complement to be finite, then Z, their union, would be finite. Impossible. So the only clopen sets are empty and Z. That's a classic connectedness flavor fact. We'll name it later. Wrap up for Lecture 2. Checklist you can reuse. 1. Open means in tau. 2. Closed means complement in tau. 3. In a finite space, just list complements. 4. In cofinite topology, ask, is the complement finite? That's the whole game. Great work today.